The B-21 Raider represents the United States' first sixth-generation bomber platform, designed under a development philosophy that prioritizes modularity, low observability across multi-band spectrums, and long-term adaptability against peer adversaries. Unlike legacy stealth aircraft, the B-21 is engineered not as a fixed asset, but as a continuously evolving node within a broader network-centric architecture. This program reveals very little publicly, but structural patent filings, defense budget annexes, open-source industrial reports, and congressional testimony provide enough data points to reconstruct the likely capabilities hidden beneath the Raider's matte composite skin. This analysis presents a comprehensive technical breakdown of the aircraft's design philosophy, signature management architecture, propulsion characteristics, avionics stack, sensor fusion systems, networking protocols, weapons integration pathway, and sustainment infrastructure.
Section 1. Airframe and Multi-Spectrum Stealth Engineering, 1:30 to 9 o'clock. 1.1. Sixth-Generation Stealth Philosophy. The B-21 departs from classic stealth aircraft modeling. Instead of minimizing radar cross-section, RCS, in fixed geometric bands, it employs multi-domain stealth. RF low observability, IR suppression, acoustic masking, visual spectrum deception, cyber electromagnetic emission minimization. This indicates a platform engineered to survive in environments dense with advanced peer detection systems such as over-the-horizon radars, quantum radar prototypes, and space-based IR arrays. 1.2. Planform alignment and edge continuity. The aircraft preserves the flying wing lineage of the B-2, but with refined control surfaces and tighter trailing edge curvature. Current imagery indicates continuous curvature eliminating angle discontinuities, distributed load-bearing composite ribs, reduced access panel edge lengths to preserve signature continuity. These features suggest optimized shaping for high-band radar threats, Ku-K, and medium-band systems, SC. 1.3. Classified composite material stock. While composition details are classified, aerospace procurement records reference next-gen polymer matrix composite batches and ceramic microsphere laminates. These materials serve to absorb RF energy, dissipate heat uniformly, resist structural fatigue under thermal cycling. The likely presence of carbon nanotubes and dielectric metamaterial placements further supports multi-directional signal attenuation. 1.5. IR suppression and thermal masking. The Raider's infrared signature is engineered around deeply buried propulsion channels, multi-stage mixing ejectors, ceramic-based heat diffusion tiles, real-time thermal contour management. This places the IR signature closer to environmental baselines, critical against modern dual-band IRST systems. 1.5. Acoustic and vibration attenuation. Defense research procurement lists vibration-isolating actuator mounts and acoustic dampening polymer sheets. These reduce mechanical noise, aeroelastic resonance, structural oscillation harmonics. This increases survivability against low-frequency acoustic detection grids deployed by peer states.
Section 2. Propulsion architecture and power systems, 9 o'clock to 16 o'clock. 2.1. Next-generation low observable propulsion. Although engine designation remains undisclosed, the propulsion system likely derives from the adaptive cycle engine lineage, e.g. AETP technologies. Key traits: variable bypass ratio, on-demand thermal management, enhanced fuel efficiency at extended ranges. The buried inlets suggest heavy shielding of engine face radar returns through serpentine ducts. 2.2. Thermal efficiency and range multipliers. Adaptive cycle engines provide 25% improved fuel efficiency, larger operational radius without refueling, high thrust mode for penetration and escape phases. Given operational necessity over contested airspace, endurance and low thermal output remain core priorities. 2.3. Electrical power generation for advanced systems. Budget annexes list high-capacity power distribution modules, suggesting architecture ready for high-output AESA arrays, directed energy self-protection, computationally heavy onboard processing. This anticipates future growth in electronic warfare and sensor fusion load. 2.4. Engine IR masking through exhaust geometry. The wide flattened exhaust likely supports rapid temperature diffusion, reduced plume visibility in MWIR/LWIR, minimized turbulence-induced signature bloom. Combined with upper surface exhaust placement, detection through ground-based IR sensors becomes significantly harder.
Section 3. Avionics Stack and Computing Architecture, 1600 to 2300. 3.1. Open Systems Architecture, OSA. The B-21 is the first bomber designed from inception to support continuous hardware refresh cycles. OSA enables quick integration of new sensors, modular software increments, rapid cybersecurity patching, reduced vendor lock-in. This ensures relevance against evolving adversary capabilities. 3.2. Distributed Processing Nodes. Internal diagrams shown in briefings suggest redundant computing clusters, localized processing for sensors, cross-linked data pipes for fusion. This reduces latency, allowing real-time threat evaluation in dense EW environments. 3.3. Mission Autonomy Layer. While not fully autonomous, the radar includes advanced decision assist tools, automated threat routing logic, predictive flight path optimization, system damage adaptive behavior. This offloads pilot workload and increases survivability during deep penetration missions. 3.4. Electromagnetic Emission Control Econ AI. An AI-driven econ suite dynamically shapes emissions, ensuring minimal detection probability by regulating LPI/LPR radar activity, controlling data link burst timing, masking electronic signatures against background clutter. This is essential for long-duration stealth missions.
Section 4. Sensor Suite and Signal Fusion, 2300 to 2900. 4.1. Multi-band AESA architecture. Imagery and defense statements indicate multi-band AESA arrays, likely including X-band for precision tracking, L-band for counter-stealth detection, possibly VHF/UHF side arrays for long-range search. These arrays operate in coordinated mode to maximize stealth and detection. 4.2. Passive detection systems. The B-21 will rely heavily on passive RF triangulation, long-range IRST, electronic support measure sensing. This reduces the need to emit active signals. 4.3. Full-spectrum sensor fusion. The avionics combine navigation data, EW threat libraries, LPI radar returns, passive sensor feeds. The aircraft creates a unified situational picture, enabling precise threat contour mapping. Section 5. Network-centric warfare integration, 2900 to 3400. 5.1. Multi-domain connectivity. The radar is a node within a vast battlefield network. It integrates with space-based ISR platforms, naval guided missile systems, joint air defense suppression networks, autonomous unmanned aircraft. This provides constant tactical awareness. 5.2. LPI/LPD tactical data links. The aircraft uses frequency agile waveforms, burst transmission, passive reception modes. This allows communication without compromising position. 5.3. Manned-unmanned teaming. The radar can command or coordinate with autonomous reconnaissance drones, EW jamming platforms, munition-carrying loyal wingmen. This turns the bomber into a strategic command node. Section 6. Weapons integration and classified payloads, 3400 to 3830. 6.1. Modular weapons bays. Weapons bays support mixed payloads, long-range stealth cruise missiles, standoff precision weapons, hypersonic glide vehicles, future, electronic attack packages. Bay architecture is optimized for multi-mission roles. 6.2. Nuclear Mission Capability, NGB program. The radar is the next-generation nuclear delivery platform. B-6112 integration,
LRSO compatibility, enhanced survivability under nuclear contested conditions. 6.3. Directed energy potential. Power allocation modules hint at future laser integration for missile defense, sensor disruption, target designation. Section 7. Sustainment, cost, and adaptability. 3830 to 4000. 7.1. Digital bomber framework. Real-time digital twins. Predictive maintenance. Automated subsystem diagnostics. 7.2. Long-term survivability. Designed for multi-decade relevance through software-driven upgrades, hardware-swappable modules, multispectral stealth renewal cycles. 7.3. Strategic impact. The B-21 alters global strike doctrine by combining persistent stealth, multi-domain integration, rapid modernization capability. This makes it the most adaptable bomber ever created.